Welcome. So this video is going to be about Euler's method, which is basically a numeric approximation of a solution curve to a differential equation. And so I've entitled it Stepping Along the Slope Field because that's essentially what we do. We've already talked about slope fields, and at this point you're good at, possibly you should be good at drawing them and interpreting them and possibly even finding a curve through them. And so the basic idea is that just like when we're drawing a slope field, when we're trying to draw a possible solution to a slope field, we pick a point and then let the slope at that point kind of direct us where to go next. But in this case, Euler's method, we're doing that only we're using little tangent line segments. So it'll look something like this. Let me blow that up a little bit. So you can see the black curve kind of represents the actual solution, and down here is the point where we started. That was the initial condition. And so basically what happens is we use the tangent line to estimate, to direct us to the next point. Then we recalculate the tangent line, which gives us a new slope, and that directs us to the next point. And then we recalculate, so at each one of these points, the line that follows it should match the tangent line at that point. So at this point, that line is supposed to follow the tangent line at that point. So you can see as this thing curves off, there's more drastic change. And so this is an approximation of the actual curve. And of course, there's error there because we're using line segments to approximate a curve, which it's never going to be completely accurate. But notice also something that's really important is the smaller the step we have, the better. Meaning that, notice this thing here looks like we're stepping about that far, right? Those should all be the same step, but which I didn't do a very good job of showing that. But we have a little change in t here that we're stepping each time. Let me start at AB. So that point right there is AB. Okay, so you can this is pictorially what it looks like. Now let's go back and talk in more detail of how this method works. So basically we start at some point. We start at a point. And we'll call it t sub k and y sub k, because what we're going to do is get a series of points. We're going to get a series of points, and we're going to, so to represent the series of points, we're going to have, a sequence of points. So we're going to use, t sub 1, y sub 1, and then t sub 2, y sub 2, and t sub 3, y sub 3, etc. So that's what this little sub k means here. Subscript is so we keep track of what points we're talking about. So we started a point, and that was like my AB over here in the drawing. And then we use tangent line, and you guys all remember doing tangent lines in Calc 1. Tangent line, tangent line segment to step to the next point. And that would be t sub k plus 1 and y sub k plus 1. So in other words, the next point in the sequence. So if we were to look back at the picture, this my a b, that would be my t sub 1 comma k sub 1. Then this right here would be my t sub 2 comma k sub 2. Then that one right there would be my t sub 3 comma k sub 3, etc. And so basically I'm just stepping along, kind of trying to approximate the curve using these straight line segments. Okay? And as we mentioned in the drawing, of course, the smaller the step, the better the approximation. So generally what we do is we establish the the step ahead of time, and we'll call that little change in t. So that would be represented in this drawing up here. Again, I drew them in, right? We're going to do some little change in t. So that's how far we're stepping this way. Then the tangent line will determine how far we step up. But each time we're going to step over. And like I said, I didn't draw these very good. They should have been the same distance each time. So we're going to step the same distance in the t direction, or in the independent variable. And then the tangent line will determine how far we step up in the other direction. Okay? So the question is, how do we get from t sub 1? So we want to go from t sub k, comma y sub k. So the first one, how do we get that to the next one? Y k plus 1. Okay? Now, to get from t sub k to t sub k plus 1, we're just going to add the little change in t. That should be pretty straightforward, right? Because we're just moving over, we're moving in the independent variable direction the same step all the time. So we're just going to do t sub 1 plus change in t gives me t sub 2, and then t sub 2 plus the change in t gives me t sub 3, etc. So that's how I'm stepping along in the positive, in the x direction, or in this case the t coordinate. And so the challenge of this method is, what do you do with y sub k to ultimately get to y sub k plus 1? And this is where the tangent line approximation comes in. So remember, a tangent line is literally a line, so it's just y equals mx plus b. And in this case, the b is going to be my y sub k, because that's my starting value. If you remember from a tangent line, the way you find the slope is by the derivative at that point. So in this case, and of course the future y is my y sub k plus 1. So the kick here is this slope is going to be defined by the slope is going to be defined by my differential equation. A little bit more room here. And then the thing we're plugging into x's is the little change in x. Oh, I'm sorry, I'm using t, so it'd be a change in t. So that produces my equation for getting from y sub k to y sub k plus 1. So again, you're going to take y sub k and you're going to add to it the function from the derivative from the differential equation, that's my slope, and then we're multiplying that by the change in t, because that's how far we're going in the independent variable direction. So this is my slope, this is my kind of b if you think about y equals mx plus b. So essentially what it comes down to, again, just to sum that up, we're starting at this little point. We're going to go over change in t, and then the question is, how far do we go up? Well, that's going to be my that's going to be my slope evaluated at t sub k comma y sub k times the change in x. And that should give me the little line segment that I'm looking for. Okay, so let's take a look at an example. So dy dt is equal to 2y minus 1, for example. And let's say y evaluated at 0 is equal to 1. And we're going to do a stepped value of change in t equal to 0.1. Okay, so probably the best way to do this is to set up a table and then kind of graph your results later. But I'm going to set up a little table here that says we got my k, my t sub k, my y sub k, and my derivative evaluated at t sub k, comma y sub k. So that's in general what the way I'm always going to label my table. So this expression here, of course, is just the 2y minus 1, because that's the function that my derivative is set equal to. So that's how I would find the derivative of y. So then we're just going to start with 0. So the initial point is going to be this one that's given to us up here. That's going to be 0 for my t and 1 for my y. And so if we evaluate the slope at that point is just going to be 2 times 1 minus 1, which would be 1. So that's my first step. That's my starting point. And this right here is the slope that's going to help me get the next point. So then we're going to go to the next point. So the next point is going to be, we're stepping up by 0.1, right? So 0 plus 0.1 would be 0.1. Now how do I get this y? Well, my y is going to be my initial y plus the slope, which is that guy right there, times the change in t, which is 0.1. So just to make that clear, that guy is right there. And this guy, whoops, that's not what I wanted. This guy is coming from that thing we decided at the very beginning that the change in t would be 0.1. Okay? And of course, 1 plus 1 times 0.1, that would just be 1.1. So that means my new point, so far I went from 0, 1, I followed a little line segment, or tangent line, and got to 0.1, 1.1. And that's what has happened so far. And so then we're going to calculate the slope at this new point so that we can find the next tangent line. And of course, the slope at this new point is going to be, I'm going to plug my y value in there, because this is only determined by y value. So I plug a 1.1 in there, and I get 2.2 minus 1, which would be 2.2 minus 1, yeah, which would be 1.2. Okay? So this is the slope. Let me put that up here so we remember. This is the slope of my tangent line. So I'm going to go to the next point. And now we're looking for so we start with initial. This is the first point after the initial. Now we're looking for the second point. Okay, so the t's are going to step up by 0.1, so that's 0.2. And the y is going to step up based on the tangent line, so I'll take the old y, which is 1.1. I'm going to add to it the slope, 1.2, times the step-up value, which is 0.1. If we do all that, we get 1.22. And then, of course, we've got to calculate the slope again. The slope is, remember, 2y minus 1, so that'd be 2 times that, which would be 2.44 minus 1, which would be 1.44. And that's my new slope. And we do it all over again. So the third point is going to be step up by 0.1 again, so that's 0.3. And I'm going to calculate my new y value, which would be 1.22, plus the slope from last time, 1.44, times 0.1. And if we add that together, we get 1.364. And then we calculate our new slope. That'd be 2 times that, minus 1, which would be 1.728. And you can see this is somewhat tedious, but it's not too hard. I mean, we're just doing some arithmetic. The key is to kind of get that pattern down and sort of get a rhythm doing. So let's do one more here. So this would be step up by 0.1, so that'd be 0.4. I'm going to take my old y value, which is 1.364. I'm going to add to that the slope, 1.728 times 0.1, and that should give me a new y value. 1.534. And etc. So we could plug that into my function again, get my slope again. You could see how you could just keep working along this, and you're doing step by step. And then it's always fun to go back and draw each one of these segments. And so you get a picture of what the graph looks like. Or you could just, maybe you're interested in knowing where your solution is at. You know, let's say you're given the point 0, 1, and you want to know what's happening with your solution when you get to x equals 1, or t equals 1, I guess in this case. You know, that might be a question that you could use the Euler's method to answer. And of course, we're approximating because we know we're evaluating, or we're modeling curved lines with straight line segments. But nonetheless, if we have small enough step values, this could be a decent approximation. All right, so that's Euler's method. Have fun with it.